Thank you very much.
All right. Well, hello, everyone. Yeah, I'm Alejandro. And I'm going to be talking about some benefits that you get from multi-concurrent proposal. It's a proposal to get censorship, resistance, MEP protection, and privacy, for some definition of privacy, in multi-concurrent proposal systems. For that, let me explain first what multi-concurrent proposals are. So actually, Ethereum resembles more a chain like in the bottom. And this is kind of like most chains a few years ago, 4 years ago, most chains will have resembled this. Nowadays, chains are resembling more, I think, like kind of like the thing at the top. And to explain the difference, what we have here at the bottom is one leader. So in every view of the protocol, in Ethereum, you have every slot. You have one leader that has full ordering rights, right? It's the one who decides what's going to be the next block. And then you have some round of voting that is decentralized, right? Where more validators are involved. In an MCP kind of chain or consensus protocol, you have something more like at the top, where you have different validators proposing different mini blocks or different proposals, and then they get merged together into one block for this particular slot. And in the case of this protocol, at the end, the first one, so V0 and V2, are the ones that are decided, and that composes the block. There are some proposals to make Ethereum MCP. The famous ones have been Fossil with inclusion list, and more importantly, braids that directly propose to have multiple proposals at each slot. And the reason why they're important is because they bring censorship resistance, right? And in the sense that, and MEP protection as well, in the sense that if I'm a user, I don't rely on one proposer. I don't have to imagine I see some trading opportunity and I send the transaction, but the next proposer can basically get MEP from me, right? That's why the whole flashbot things and Ts and whatnot. But protocol level, they can do that, right? Because they have full ordering right. So thanks to MCP, thanks to multi-concurrent proposers, I can send my transaction to multiple users. And then I can ensure that as long as one of them includes my transaction, I will be able to exploit that opportunity. And even in that case, this one proposer might not be so easily able to exploit my transaction because it needs to include this block within some time limit in order to beat the other concurrent proposers. But so what I want to claim is that there's this like unavoidable trade-off between, even in multi-concurrent proposer systems, there's this unavoidable trade-off between censorship resistance, reasonable pricing of my transaction, and low latency. And the reason is, if I want to get censorship resistance and reasonable pricing, what I do is I send the transaction to one proposer, right? What can happen is that this one proposer censors me, and so I can try in the next slot with a new proposer, but then I don't get low latency, right? If I want to get reasonable pricing and low latency, then I only try once, and then if that proposer doesn't include my transaction, I just consider that opportunity, trading opportunity, perhaps I just missed it, and I'll just try next time with another one for another proposer, right? But in that case, I don't get censorship resistance. And if I want to get censorship resistance and low latency, then I can send the transaction to all the proposers. But then there's a possibility that all the proposers include my transaction. And somebody has to pay for that. Because if nobody pays for that, if that is free, then attackers can exploit that, right? And reduce the good put of the system, the useful throughput in the system. So if you can think, for example, if your system has 100,000 transactions per second, and everybody sends the same transaction to 5 different proposers, then the good put is a fifth of that. It's 20,000 transactions per second. And so there's a number of chains that are MCP. I should actually add Solana now here, or say Giga, Hedera, Falco, and Aptos. So they're all multi-concurrent proposals. So they have this difficult choice of what do they do, who pays for the possibility of multiple transactions being included. And in the case of Hedera, they're actually charging users for that. So if a transaction appears multiple times, the user pays multiple times the transaction fee. Interestingly, even for execution, which shouldn't really be the case because the transaction is definitely only executed once. But you should pay for ordering, right? They probably do this because I suspect they don't have multidimensional fees. And in the case of Falco and Aptos or Sui, which are systems in production, the user only pays once, even if the transaction appears multiple times. And I have seen cases of Falcon transactions appearing 10 times in the system and only being charged for once. So it's an incredible attack vector, right? Why is this not a bigger problem? In Falcon, it's a wholly different kind of reason, but in Aptos, Sui, or Hedera, it's not a big problem because transactions are being sent through trusted RPCs. So it's the trusted RPCs the ones that are in charge of deduplicating the transactions, making sure that they are targeting a replication factor of the transactions that is within the goals of the system. But as a user, if you bypass the RPCs and decided to send transactions directly to validators, you could actually exploit this in the case of Sui and Aptos and severely decrease the output of the system, severely. So I like to see the evolution of censorship resistance in kind of like this way. So first, we have leader-based consensus, right? It's like what Ethereum has at the moment, right, with the slots, and just one proposer per slot. Then the proposal to have multi-concurrent proposers and providing censorship resistance. This is where I would place Aptos, Sui, or Filecoin. Then the realization that it shouldn't be free to have the transaction duplicated. It shouldn't come for free to the user. So charge users for denial of service resistance on the system side. But then also realize that that implies that it's too expensive for the user to use the benefits of censorship resistance. And in that case, what we're proposing, as say, is to actually shard the transactions. So instead of sending the same transaction to, so this is how it will work at the moment in Sui, Aptos, etc., Solana. What you do is if you want to exploit the benefits of censorship resistance, what you do is you send the same transaction to multiple proposers, right? And as long, in this case, this user sends to 3, meaning that as long as no more than 2 censors the transaction, your transaction will be included in the next lot. The problem is this doesn't scale, right? The problem that I just explained. What we're proposing to do with Sedna at say Giga is to shard the transaction and send different shards to different proposers, such that if enough of them include the transaction, they actually get the benefits of censorship resistance. But because the shards are a fraction of the size of a real transaction, the cost of ordering that amount of bytes is much lower. And we actually approximate the information theoretic bound. I'm going to show, basically, the nice thing about this as well is that it's completely protocol agnostic. So it's completely, let's say, like a client-facing, a user-facing protocol. So the user can decide what are the parameters that they want in terms of censorship resistance, pretty much like now, right? Like the user can decide, in an MCP system, he can decide to send a transaction to one proposer, to multiple proposers, resend it, whatever. But now he can do that as well with parameters that imply the sharding. So how many shards he sends, how many shards are needed to reconstruct the transaction, etc. The properties that we get, of course, are safety and liveness. So it's impossible to, for different proposers to reconstruct different transactions if they get different shards or something like that. But in any case, all the shards are being ordered. So there even is a deterministic execution order, much like in any chain. Of course, liveness as well, so there's a number of shards after which reconstruction is overwhelmingly probable, likely. This, of course, is deterministic liveness for erasure coding, but we have a solution with rateless codes, which are faster, but they give you a small, negligible probability of no reconstruction. In any case, this is something that, so if the transaction is not reconstructible, as I said, nobody can reconstruct it. So in that case, the user can just resend it or keep sending more rateless codes. And here's an interesting properties that actually, when we started working into this, to reduce that problem of the cost of censorship resistance, both in terms of output for the system, but also in terms of like fee cost for the user. But we started getting some nice properties, because it turns out that because you're sending shards to different proposers, no proposer knows the content of the transaction. So you start getting similar properties that you get with encrypted mempools for some applications, because at the moment of ordering the transaction, the shards, the proposers do not know the content of it. And it actually can be analyzed to exploit and to get MEV resistance. And I'm going to explain that in a minute. And also to get privacy. What I'm showing here is for some parameters. Again, it has a number of parameters that I'm not going to get into details. But how many, what is the adversarial assumption that you have? So how many proposers you want to tolerate censorship against? Do you think there's just one proposer that might be censoring you and you don't know which one it is? Is it 20% of all the proposers what is the cost of this transaction in terms of MEV. So how much MEV can be exploited if the transaction is reconstructed before the transaction is included, etc. But what I'm showing here is for some standard parameters, as the something interesting to note is that actually, if the transaction is very, very small, it actually pays off to just duplicate the transaction. Because it's so small and there's some overhead of metadata to identify each shard that it may not pay off to just split the transaction in small shards if the transaction is already so small. But this, very quickly, as soon as the number of bytes in the transaction increases slightly, it pays off a lot more to just shard the transaction, to get the same amount of censorship resistance. And as the transaction size increases in size, our solution actually approximates the information theoretic lower bound. So basically, you cannot get better replication factor in order to tolerate an adversary censoring you of the same size. Of course, the bigger the adversary that you want to tolerate in terms of censoring your transaction it is, the more that you're going to need to shard the transaction. The bigger the shards are going to have to be. But in any case, they always approximate the information theoretic lower bound for whatever adversary as the transaction size increases. And in terms of latency, which is an important thing, this is, as I was mentioning, you get interesting properties that are similar to encrypted mempools. In like a number of encrypted mempool solutions, latency is kind of a concern, especially now you have a number of chains like SeiGiga or Sui. After all of these chains are also really focused on low latency. And if encrypted transactions increase latency by a few tens or a few hundred milliseconds, that is huge, right? And the nice thing about sharding with erasure codes, and especially with rateless codes, is that the latency added to it is negligible. We're talking here, if you see at the y-axis, we're talking about 1 to 3 milliseconds. So this is like negligible. And in some cases, actually, because of the reduction in transaction on the broadcasting, the number of bytes that are being broadcast to the number of proposals is actually faster than just replicating the full transaction payload. So I have said that Sedna provides this number of properties, but I said that it depends on some of the assumptions, right? And so let me get a little bit more into the details of how we tolerate an adversary that's trying to reconstruct the transaction. So it's trying to get enough shards before the transaction is on-chain so that it can see the content and try to exploit MEV out of it. So basically, what is the MEV protection that this sharding solution, Sedna, gives you? So for that, imagine we have a number of proposers, some of which are correct. They behave. They're not trying to exploit MEV. And they just get your shards and then just validate them and include them in the block. And some that are evil. And the evil ones, the rational ones, what they're going to do is they are going to decide whether they include their shards, the shards that they get for the transaction, or withhold them in the hope that some other proposers will include their shards and they can download those shards and reconstruct the transaction locally. And only then decide whether they include the transaction and in what order. So, of course, the user has one important parameter, which is how many shards it sends and how many shards are needed for reconstruction. The difference between them is the slack. So how many shards you can afford to be censored. So if you send 10 shards and 7 are needed for reconstruction, you have a slack of 3, right? You can tolerate 2 transactions being, 2 shards being censored, because still you still have 8 that will be included. Actually, the slack was 3, sorry. So in this case, imagine there's one of the evil proposers that doesn't include your shard, but you can still reconstruct the transaction. But the moment the second evil proposer doesn't include the shard that you gave to him, the transaction is not included. So you get a slack of 1. That's the slack of this transaction. And there are 2 risks for MEV reconstruction. As I said, the MEV exploiting from the proposers. As I said, there's the MEV is exploited in this protocol when the transaction can be reconstructed by these attackers within enough time before it appears on-chain. And so there's 2 ways that they can do this. One is withhold the shards for one entire round of consensus, which is the multi-slot delay that I just showed, or actually decide that they're going to include their shard, but only at the very end of the round of consensus, and try to play a timing game try and see if they can see some shards before that. And that's the within slot risk. The interesting bit is that they're actually at odds in terms of the properties that you want to. So if you want to provide MEV protection against multi-slot delay risk, what you want to get is a high slack. So you want to distribute a lot of shards such that only a few of them are needed for reconstruction. That guarantees to you, as a user, that your transaction will be included in this slot. But that also means that a small adversary has a high chance of reconstructing the transaction quickly within the slot. So it's easier for the attacker to reconstruct the transaction at the beginning of, if it was Ethereum, let's say, at the beginning of the 12 seconds, and exploit that for MEV within those 12 seconds. So there's kind of like dots. So let's look at things that we can do to alleviate this trade-off between within slot delay risk and multi-slot delay risk. The first one is what we call the ratchet strategy. So a problem that appears is that in the naive protocol, if you send a number of shards and some of them don't get included in this slot, you need to send more shards, right, in the next slot in order to include your transaction, in order to pay off for the ones that were not included. In a naive way, you just choose randomly again and send some shards to some proposers. But of course, if you're a smart user, what you can do is what we call the ratchet strategy. And so in the ratchet strategy, what you can do is just learn from the fact that some proposers did not include your transaction and just not send shards to them, right? And that means that there's kind of like a punishment for these proposers that didn't include your transaction, and that, assuming a static adversary, dramatically increases the probability that your transaction will be included in the next slot. So here's how the ratchet strategy improves the probability of inclusion. So in red will be the naive approach, where you just randomly choose some proposers. And in blue is the approach where you learn from the proposers that are censoring you and not send the transactions to them. So basically, as there are more failed slots in the naive approach, the probability of your transaction just not succeeding and being delayed further increases, whereas in the ratchet strategy, it resets to the original probability. The other thing that we learned, and this one I really like because it's a really interesting rational property, is what we call pivot K. So another thing that occurs is, in this case, there's two types of people participants, right? So we have a cartel here of 3 participants that are going to collaborate with each other, right? They're going to send their shards to each other so that they can reconstruct the transaction and exploit MEV together. And then they share the MEV. But something interesting occurs, which is the one at the bottom gets its share of MEV and also behaves correctly in the view of everyone else. So it gets paid for the fees. It doesn't get punished in any way. So it's kind of like an asymmetric relationship with the other rationals, right? And so nobody really wants to be the one out of the cartel, out of the self-interested rationals that collude together in order to reconstruct the transaction to exploit MEV. Nobody wants to be the one that does not actually behave correctly because he can get punished, right? This is what we call a baiting strategy in rational distributed game theory, which is a particular type of punishment strategy. And this already is a play with just the fees for the transaction. But the fees for the transaction they are paid for every shard that is included, whether that shard is important for reconstruction or not. And so what we do is we exploit further this property with what we call the pivot K bounty. The pivot K bounty means we're going to give an extra fee to the first K shards, where K is the number of shards needed for reconstruction. So if there are more shards included, they get the normal fee, but they don't get the bounty. So that puts even more pressure on evil participants to behave, and not only to include the shard, but to include the shard in a way that is meaningful. Yeah, okay. Yeah, with that in mind, here are some results. The takeaway from these results is the last column in the last table, which basically says, well, actually the last row, which basically says that in order to protect $5,000 of MEV risk, so suppose you have a transaction where you're doing some trade that if someone was able to see, imagine it's a trade on some AMM, and if somebody was able to see the transaction and front run it, then they could steal $5,000 from you. And in that transaction, using Sedna, using the pivot K bounty, using the ratchet strategy, etc., and in a way that I want, and setting the parameters right, it only costs $2 to protect from the attacker. So with $2, you secure $5,000, and that scales, right? For $5 million, just $200 will protect you. Sorry, just $2,000 will protect you. As future work, we're looking into, I kind of lied when I said that there was privacy and MEV protection. The truth is, if you get a number of shards that is not, like if you're an attacker and you get a number of shards that is not enough to fully reconstruct the transaction, in the normal erasure codes, you can actually start learning information about the transaction. We actually have a paper almost ready on providing nonlinear decoding until you have the full decode threshold. So actually learning pretty much nothing about the transaction. So I'm really getting properties that are very, very similar to what the encrypted mempools give you, while preserving the same latency. Of course, we're also, another interesting bit is how you price this ordering, this distribution of different shards. And yeah, threshold attacks as well. So yeah, that was all. Thank you. So if you have any question.
Are there any questions? No. So if there are no questions, thank you very much.
Thank you.